Hello everyone. In this narrated presentation, I'm just going to give you a lecture on the final topic in thermodynamics. So this is the first law of thermodynamics, especially in open system. So let's have a review about what's the difference between a closed system and an open system. So a closed system basically means that the system is closed and the mass is fixed inside that system. So if we think about we have a boundary, so think about an example of a balloon or just a bottle with a sealed cap. Okay, so everything is sealed inside that within that boundary, so there's no mass transfer across the boundary of the system. And also can have a look at another example with what we call it a cylinder and a piston arrangement. So think about if we have a leak-tight piston, so there will be no mass leakage here, and then the mass inside that cylinder will be kept constant during any process. So we call this is a closed system. However, in an open system, the mass is allowed to cross the boundary of that system. So let's have a look. Assume that we have a pipe flow like that. Okay, so if we define a control volume with the boundaries, so these two boundaries are the wall of the pipe. So obviously the mass cannot flow across that boundaries. However, if we have an inlet and if we have an outlet, so the mass can go across this boundary from the inlet and exit from the outlet. So in this case, for an open system, we will have a mass flow, mass flow from the inlet to the outlet. Let's have a look at another example of a hairdryer. So the air, this is the inlet for the air to go inside this hairdryer, get heated, and then exit from the outlet of the hairdryer. So in any open system, we're not talking about a fixed mass inside that system, and then we are talking about the mass flow rate, which is defined by how much mass will be flowed through this system in a fixed time period, for example, per second. So we already know that to change the internal energy of a system, we have two methods to change. So one is called work transfer, another one is called heat transfer. And in the first topic, we have learned how to calculate the work transfer in a closed system, by using this formula. So the work done is equal to P times dV, and we do the integration from the initial point to the end point. And then we actually can give it a name. So this type of work, we can call it shaft work. And in an open system, the difference is that we will have two types of work transfer. So the first type will still be shaft work. So this is actually the same to the work transfer when we talk about in the closed system. So that's the same. And we will have an additional flow work, especially for open system. So this flow work occurs by virtue of a fluid entering or leaving an open system. So this is an additional item we need to consider, especially for an open system. Now let's have a look at how can we derive the flow work, especially for the open system. Let's consider about just a pipe flow. And then we think about one is inlet and two is outlet. So we think about a mass of delta M, so which is a small mass the small mass is going to enter from the inlet 1, crossing the system boundary here, and it will leave the system at the boundary of the plane 2. Okay, so when the mass enters the system, and the mass in front of it will be displaced, so that we can calculate the work done on the system, delta W, which is equal to the force times the displacement. So the force is the pressure, P, times the area. So that's the force, okay? And the force times a small distance, which is delta L, so that we can calculate the small work done during this process. And also, we can have a look at that. The area here, okay, area here, times the small distance, actually give us the volume of that small volume. Okay, so that is equal to the volume, V1. And we also know that if we define a specific volume at the inlet, so this specific volume will be just equal to the capital volume, the total volume, divided by the small mass. Okay, so this is a general definition of any specific term, such as specific volume. So therefore, we can write A times delta L, which is V, and is equal to the small mass times the specific volume. So that finally we get this one, which is in yellow background. So this defines the flow work. Okay, so the flow work can be defined by delta M, so the mass times P times V. Okay, so in closed system, we need to be careful about what's the difference between closed system and an open system when we're talking about the mass here. Okay, for any open system, we're not talking about a fixed mass, and we need to think about the mass flow rate. So the mass flow rate can be defined by the dm divided by dt, and we will put a dot on top of the m to show the difference. So this is a differential form, means that this is a rate of the mass flow, so usually in the unit of kilogram per second. So now we can write the equation like that, and then we're going to put dots, okay, on the top of the work done, and also on top of the mass transfer, mass flow rate. Okay, so here, because we already put a dot on, this is actually the rate of work transfer, and the unit for that will be watt. And here we put a dot on top of the mass, which gives us this is the mass flow rate in the unit of kilogram per second. So we can write this equation according to different points. So we can write it on the inlet, or we can write it to the outlet. So now, as I explained earlier, for an open system, the total work is the sum of the shaft work plus the flow work. Okay, so this is a form of how I'm going to write the flow work is equal to m times p times v. Okay, in an open system, we have already derived how to calculate the flow work. And for convenience, we are going to think about, we're going to regard this flow work as a kind of another additional form of energy. Okay, as we have learned in the topic of the closed system, we know that the total energy of that system consists of the kinetic energy, potential energy, and the internal energy. So, for the open system, we just consider about an additional energy form, okay, which is a flow work, and we just derived how to write the flow work. So it's m dot times P times V, so that in an open system, the total work, the total energy of that system, we will have 4 components. So they are kinetic energy, potential energy, internal energy, and the flow work. And also we can define the specific total energy E here for the open system by dividing m dot on both sides. So then on the left hand side, we're just going to specify a specific total energy. We're going to use a lowercase e, which is equal to E dot divided by m dot. Okay, and then finally we can get this formula. Okay, so that's a specific total energy, specific kinetic energy, specific potential energy, specific internal energy, and a specific flow work. So this is a definition of what we call it enthalpy. So as you can see that from the last previous slide, we can see this compilation. So this compilation U plus PV actually occurs quite a lot of times. So this is just for convenience, we're going to introduce a new property called enthalpy. So this is defined just by the sum of internal energy and the PV here. So we just define another property which is called enthalpy, and this enthalpy is especially very important, especially for the open system, so we're going to use this very often. So now once we have defined enthalpy, and then we can replace this term U plus PV by H, so that the total energy will be the sum of the kinetic energy plus potential energy plus enthalpy. As we have learned in the first topic, the first law of thermodynamics for a closed system. So this is how we're going to write that formula. Okay, so the heat transfer subjects the work transfer, which is equal to the change in the total energy. Okay, and similarly, we can actually write that equation for an open system as well. However, we need to make some changes. The biggest change is that we're going to put all dots, you see, all these dots on the top of each term. So this will give us the unit of the rate of energy transfer or the rate of the change in the total energy. So everything will be in watt or kilowatt. So similar to the closed system, we must identify all forms of the energy so that are of interest to us. So we need to think about the different energy forms inside that, and then we think about the magnitude, the relative magnitude of different terms, and think about how many terms can be ignored. And again, here I would remind that flow work is actually in open system is considered as a form of energy, so it's already included in here and not here. So now we can write the first law of thermodynamics for open system like that. Okay, and then we think about the different forms inside the total energy for the outlet and also for the inlet. So that we can write for the outlet E2 dot, so I'm using M2 dot times the total energy here. Okay, so we can see I have already using enthalpy, subject the inlet mass flow rate and the different forms of energy at the inlet. So if we assume that M1 dot is equal to M2 dot, so these two mass flow rates are exactly the same at the steady flow condition. Okay, so now M1 dot, M2 dot is the same, so we can just use M dot for that. Okay, and then we can rearrange everything so that we get a final equation like that. So this is a final equation, okay, in yellow background. I think this is the most important equation to describe the first law of thermodynamics for an open system. And then we can have a look at it, because we have different terms in here, so we just look at it, each of these. Okay, so the first one is a heat transfer. Okay, heat transfer during the process from 1 to 2, and this is actually the rate of heat transfer, so it has got the unit of power, for example, the watt or kilowatt. Subject the work transfer during the process from 1 to 2, and also this is the rate of work transfer, and also have the unit of watt or kilowatt. And here m dot is the mass flow rate, so it has a unit of kilogram per second. Here, this is the difference. Okay, so this is the difference in enthalpy, and this is the difference in kinetic energy, and this is the difference in potential energy. Okay, so this equation is known as steady flow energy equation. So we use SFEE for the short term. Steady flow means that mass flow rate at the inlet and the outlet are exactly the same. So you can see that this equation is actually quite long, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 variables inside that equation. And when we are going to apply this equation to different practical situations, so we need to investigate all these magnitude of these variables to see. Probably sometimes some of these terms can be negligible. For instance, so here I listed some of these instances. So for example, when the system is very well insulated, for example, and then you can imagine that there's no heat transfer, okay, no heat transfer across the boundary, and then we actually give it a name, so it's an adiabatic system. So once you see this word, this term, okay, so that just means that this is very well insulated and the heat transfer is 0. So we can ignore heat transfer if it is an adiabatic system. The second, sometimes if the system is not doing work to the surroundings, or the surroundings is not doing work to the system, basically means that there's no work transfer during any process. So in that case, we're going to assume that the work transfer here is 0. The third one, Z1 is equal to Z2. Okay, here. This means that at the inlet and the outlet, the difference between the height of the inlet and the outlet are very small, so that we can ignore the difference in there. I think this condition applies to most applications considered in this module. So this is almost all correct for every application that we're talking about in the following slides. Right, in this slide, I just listed both equations. The first one for open system, the second one for closed system. And then we just want to give you a comparison between these two equations. So there are two big differences here, okay, as I already highlighted. The first one is that for each of these heat transfer, work transfer, and mass, for open system, we all have dots on top of it, so that they are rates, okay. They are rate of heat transfer, rate of work transfer, and the rate of mass flow. And they're in the unit of watt or kilowatt. Okay. However, for a closed system, we're talking about a fixed mass, so they must be in the unit of kilogram, for example. And the second difference is that here, okay, for an open system, we're using the change in enthalpy instead of change in the internal energy for a closed system. So that's the second difference. And all the others you can see here, right? These two terms are exactly the same. So they're both the change in the kinetic energy and also the change in the potential energy. Right, okay. So now what we're going to do is that we're going to apply the steady flow energy equation to different applications. So these applications considered in this module, we will have a total of about six applications. Okay, so 6 different devices we're talking about. And first of all, we need to think about the function of each device. So what they are designed for. What's the basic function of this device, so that we can better understand the following discussion. So the first device is called nozzle. Okay, so you can see from this diagram, for a nozzle, you can see the change in the area, cross-sectional area. Okay, and then at the inlet, we normally use a subscript 1 for the inlet, and then we're going to use a subscript 2 for the outlet. So you can see that the inlet area is higher than the outlet area. And this will give an increase in the velocity. So the velocity at the outlet, we use C2, okay, is higher than the inlet. And if the nozzle is very well insulated, we can consider that the heat transfer is 0, means that there's no heat loss across these boundaries. And especially important is that for a nozzle, the mass flow rate is constant. So we think about the mass flow rate here, m1 dot, is equal to m2 dot. Therefore, we can write this equation in the yellow background. This is a very important equation for us to calculate the cross-sectional area, for example, at the outlet A2. Okay, you can have a look. Basically, the mass flow rate is equal to the density times the volume flow rate. And also, the volume flow rate can be written in the production of the area and the velocity. So I can write these two because they are the same. As I said, this is steady flow. Okay. And then we can also write by using specific volume here. Okay. So as you can see that the density is defined as the mass over the volume. And the specific volume is defined as the volume over the mass. So you can see that the density and the specific volume, they are in the inverse relationship. So they are inverse to each other. Okay. So in this module, actually we use specific volume more often than density. Okay. So these two, I would say these two are most common, most often used when we calculate the mass flow rate. For example, when the mass flow rate is given, and C2 is given, V2 is given, and then we'll be able to calculate the cross-sectional area at the outlet. Okay, in this slide, I just give you some images for you to understand what's the application of a nozzle. So you can see here, with the change in the cross-sectional area, we can effectively improve or increase, the air velocity, for example. Okay, so the air has been accelerated inside that nozzle, and at the outlet, we have a much higher air velocity, and this high velocity can be used in the test of, for example, automobile, where if we think about how to test its aerodynamics around a car, okay, and then we can use that nozzle to generate a very high speed of air flow here. Okay, so this is a nozzle. You can see the inlet area is higher than the outlet area. There's another device called a diffuser. So diffuser is actually just another device which is operating the opposite way of how a nozzle is working. So you can see the inlet area is smaller than the outlet area, so that the air velocity will be decreased when it goes through a diffuser. So now what we're going to do is that we're going to write this equation, because this is a very general equation and it applies to every open system. Okay, And based on the application of a nozzle, so we just need to make some reasonable assumptions so that we can simplify that equation based on these assumptions. So the first assumption we can make is that we can assume this system is insulated very well, so that this is an adiabatic process, and then we can ignore the heat transfer during this process. And also, as you can see from the previous image, that a nozzle is basically designed to increase the air velocity, so that it's not designed to output any work, and there's no work done to the system at the same time, so that we can give another estimation that the work transfer during inside a nozzle can also be ignored. The third assumption is that the change in the position of inlet and outlet are very small, so we can ignore that, comparing to the change in the velocities. So this term, the magnitude of that term is relatively much smaller than this one or that one, so we can ignore the third term. So based on these three assumptions, let's have a look. If Q is 0, okay, so we can cross that out. If W is 0, we can cross that out. So that on the left hand side, we will get 0. Okay, so M dot must times a 0 to get 0, means that inside here, these three terms must be 0. As I said, this term we have already ignored, means that H2 subtract H1 plus half of C2 squared subtract C1 squared, so these two terms has to be 0. So now we can write a simplified equation like that, okay? Or we can rearrange it, so put all the variables here at the outlet is equal to all the variables on the inlet. So this is a simplified form of the steady flow energy equation, especially for the nozzle. And I would say this is very useful when we're calculating any questions about the nozzle. Okay, so here we have another device called a throttle. So throttle, you can see that we have some changes in the cross-sectional area, okay, here, right? So that the function of nozzle basically is just to restrict the flow. And you can see the inlet and outlet area is quite similar. So it's basically for pipe restriction or in the case of engine throttle. Okay, let's have a look at how are we going to use different assumptions to simplify that, this general steady flow energy equation. In general, for throttle, we can make the following assumptions. First of all, the heat transfer can usually be ignored. This is because of the size of the throttle is usually quite small, and it's very easy to well insulate a throttle, so that we can assume that process can be adiabatic, so the heat transfer is 0. And also for throttle is not designed for outputting any work, so that work transfer can also be 0. Okay, and because of the inlet and outlet area are quite similar, so the change in the velocity can also be ignored, and also can ignore the change in the potential energy. So that if we apply all these assumptions, we can get a very easy final equation for a throttle. Okay, basically means that the inlet and outlet enthalpy has exactly the same value. So that's a very simplified form for the nozzle. Right, okay, so in this slide I included a YouTube video. So I'm not sure if we can play YouTube video inside this video. Okay, so what I recommend you is that you can either use this title and search by yourself on YouTube, or you can use that link to have have a look at this video. Okay, so you can pause the video now and have a look before you come back to this presentation. Okay, so this is a general, very simplified schematic for how a power plant systems look like. Okay, so basically you can see we have 4 components here. Okay, we have a boiler, we have a turbine, we have a condenser, and also we have a water pump. And in the following slides, I'm going to explain all these 4 components. Okay, and how I'm going to use the steady flow energy equation for each of these devices. So the first device is called steam boiler. So steam boiler is basically used to heat up the water and then to generate steam. So sometimes we also call it a steam generator. So you can see here we have inlet. So the cold water comes through from the inlet and flow inside that boiler. Okay, so by burning some kind of different kinds of fuel, for example, coal or natural gas, the water will absorb heat from combustion of the gas of different fuel, and the water will be evaporated into steam. And then steam will exit the steam boiler at the outlet. As you can see here, the steam boiler basically, you can regard this as a kind of a huge, massive heat exchanger. Okay, so the water will gain heat and then change to steam. So this is basically a heat exchanger, which means that the heat transfer inside this unit is very important. So now we start again from this general equation. So as I just explained, in the steam boiler, water enters the boiler and is heated, and then it evaporates to steam, so that the heat transfer inside a steam boiler is massive. So the heat transfer is definitely not zero. And also can make the following assumptions, because the boiler is not designed to output work. Okay, so it's basically a heat exchanger, so that the work transfer here can be ignored. And the change in potential energy can also be ignored. The changes in kinetic energy sometimes is also very small if we compare with the change in the enthalpy. Okay, because as I said, this is a heat exchanger. Okay, so it provides a lot of heat, so that the changes in the enthalpy is a very big value. And this usually is much bigger than the change in the kinetic energy, so that we can ignore this term as well. So finally, after we apply for all these assumptions in that general form of that steady flow energy equation, and finally we'll get a simplified form like that. So the Q dot heat transfer is equal to mass flow rate times the difference between the inlet and the outlet. Now let's have a look at the second device inside the power plant system, which is also a very important device. So we'll call this a turbine. So turbine is used to generate work basically. Okay, so the high temperature steam enters the turbine and drives the blades so that it drives the shaft, and when the shaft is connected to a generator, so that electricity will be generated. And then also we will start from this general form. So in the case of a turbine, we probably can just assume that the change in the potential energy can be ignored. And as you can understand now, the purpose of a turbine is basically mainly to produce useful work, such as electricity, so that work transfer definitely will not be zero. And it is sometimes difficult to perfectly insulate the device because a turbine is a huge device. So therefore, the heat transfer sometimes cannot be ignored. So that's the only assumption we can make, is that the change in the potential energy can also be ignored, and therefore, that SFEE now can be written in this form. You can see that only the change in potential energy here is cancelled, and we have kept all the other terms. This is the third device in the power plant system, so we call it steam condenser. So steam condenser is used to condense the steam from the turbine. Okay, coming out from the turbine, so we need to condense it to water. So at the outlet, we'll get condensed water. So basically, this is another huge heat exchanger. Okay, we're going to run the coolant from the inlet to the outlet to cool down the steam and condense the steam. So we have cold water flow in, and then the hot water come outside. Means that the heat will transfer from the steam to the coolant. For the steam condenser, the steam enters the condenser and cool down to remove its latent heat. So basically, this is another heat exchanger, and the heat transfer will definitely not be zero. And think about, the steam condenser cannot output work like a turbine is working, so that the work transfer for a steam condenser can also be ignored. And just similar as a steam boiler is working, we can again ignore the change in the potential energy, we can ignore the change in the kinetic energy. So finally, the SFEE for a steam condenser can be reduced to this form. Right, so if you compare this with a simplified form for the steam boiler, you can find that these two are exactly the same. Okay, exactly the same. The only difference is that for a steam boiler, because the heat is transferred to the system, so that the heat transfer you calculate from this equation, you will get a positive value. However, for condenser, in the case of condenser, because for inside the condenser, the heat is transferred from the hot steam to the coolant, to the surroundings, so that in this case, the heat transfer calculated from this formula, you will get a negative value. Now this is a final device inside that power plant system, so it's called a pump. So the pump can be a water pump, okay, or compressor. So the compressor can be an air compressor. So no matter it's a pump or compressor, the working fluid will go inside the system through the inlet, and the pressure will be increased, and then the working fluid will exit at the outlet. So no matter it is a pump or compressor, so we can either use a mechanical pump or compressor, or we can use an electric pump or compressor. But no matter what it is, we need a shaft work for the pump or compressor to be working. So this shaft work can be provided by, for example, the electricity. So that, in this case, the work done is definitely not zero. And also the work done is on the system by the surroundings, so that in this case, the work done is negative value. In most cases, the pump and the compressor, the size is quite small, so we can practically quite easy to insulate it, so that we can consider that the process is adiabatic process, so that the heat transfer is zero. And also we can ignore the potential energy change. we can ignore the change in the kinetic energy because the value, the magnitude of that is much smaller than the change in the enthalpy. So therefore, finally, we get this equation. Okay, so this is minus because Q in front of it, Q is 0. Okay, so Q has been cancelled. So you have minus work transfer left on the left-hand side. And this is m dot times the difference in enthalpy between the inlet and the outlet. In this slide, I have summarized all the devices we just covered. 1, 2, 3, 4, 5, 6. We have covered 6 applications, 6 devices. Okay, so in this big table, I just summarized all these assumptions, like if we can assume the work heat transfer is 0, work transfer is 0, if we can ignore the change in potential energy, if we can ignore the change in kinetic energy. So if we see a yes, Y for yes here, means that this assumption will apply to this device. Okay, so for example, for a steam boiler, the heat transfer will definitely not 0. So this assumption cannot be applicable to a steam boiler. So it's no here. And then for the turbine, the work transfer cannot be ignored. So this is definitely a no, for work transfer is 0. So this assumption is not applicable to the turbine. And in the final column, I summarized all the simplified forms, okay, for different devices here. So you can use them directly for any device, okay, in the question. However, if you don't want to remember this, you can also apply the reasonable assumptions to derive it by yourself from that general SFEE by applying all different kinds of assumptions. So again, I listed this equation especially for the case of a nozzle. Okay, I explained this earlier. So this is very important and very useful when we calculate especially the exit area at A2. So from this slide, we're going to do some examples and practice, and this will be explained in the next video. So in a separate video, I'm going to demonstrate how I'm going to calculate these examples by applying the SFEE.